The topic for today's lecture is applications of Fermi-Dirac statistics. Let's start with a degenerate Fermi gas, or talk about degenerate Fermi gases. That's a gas of fermions at a very low temperature. It could be helium-3 particles, it could be neutrons, it could be protons, electrons, whatever the case may be. We can talk about, and will talk about, applications such as white dwarf stars, neutron stars, etc. Conduction, electrons, and solids, in fact, is a really good place to start. So let's do conduction, electrons, in solids. I want to remind you of a couple definitions we did earlier on, just because we're going to probably use them again. We defined a quantum length, L sub q, as h over the square root of 2 pi m kt. And we also defined a quantum volume, V sub q, in the same way as h over square root 2 pi m kt to the third power. Okay? So, let's talk about the application of conduction, electrons, and solids. So the first thing we ask ourselves is, well, could we get away with classical statistics? If I want to apply Boltzmann statistics to an ideal gas, remember, we said that V over N had to be much, much greater than the quantum volume. Let's talk about an electron. Electron at room temperature. For electron at room temperature, we have a quantum volume, which is going to be h over 2 pi m kt, square root to the third power. That's going to give me something like 4.3 nanometers cubed. On the other hand, in a typical metal, you have one conduction electron per atom, so the volume per conduction electron, that is to say V over N, is going to be about something like 0.2 nanometers cubed. So in this case, V sub N is not much, much greater than V sub Q. In fact, it's smaller than V sub Q, so we can't use classical statistics. We've got to use Fermi-Dirac statistics. Now, even if this thing is at room temperature, the temperature is too low to use classical statistics. For all intents and purposes, we can make our life easier, and we're not going to change the problem at all appreciably if we just say, let's let t equal 0. It's an approximation, but it's actually a pretty good one. When temperature is equal to 0, all single particle states are going to be located in this way. So if I were to plot energy on the x-axis and number of particles, number of fermions on the y-axis, this is where energy is equal to the chemical potential. We call this point, by the way, we call the chemical potential in this case the Fermi energy. So that's a new word, but it means chemical potential for fermions in that case. At t equals 0, the Fermi energy is always equal to the chemical potential at t equals 0. All single particle states are going to be residing at energies less than the Fermi energy. All the states that have energies above the Fermi energy will be unoccupied. Okay? We call this a degenerate gas. Now, what the Fermi energy is depends on how many electrons happen to be present. So if we add one electron at a time to an empty box, each is going to go into the lowest possible energy state it can get into until all of them are occupied at some energy just below the Fermi energy. If I want to add even more electrons, even one more electron, I have to give it an energy equal to the chemical potential, or the Fermi energy, mu. That being the case, that tells me that mu is going to be equal to partial of the energy, we'll use capital E for energy, with respect to n at constant entropy and volume. And this works since, in this case, dE is going to be equal to mu if dN is equal to 1. I have one particle, I've got to add mu to add that one particle. We're assuming the entropy is fixed because all the electrons are in the lowest energy state anyway. So I want to calculate the Fermi energy. Assume all the electrons are free inside the box, but they're confined inside a box of side L and volume V equal to L cubed. Okay? Now, this isn't an especially great approximation for conduction electrons in a solid because they do feel some attraction in terms of ions in the lattice, but we're not going to worry about this for now. We're going to assume that that effect is small enough. So we've, again, got a particle in a box problem. Same solutions to the Schrodinger equation apply to what we did before. Sine waves are going to represent the wave functions. So in one dimension, the allowed wavelengths, then, I can write lambda sub n will be equal to 2L over n, just like the particle in a box. The allowed momenta, of course, would be h over lambda, which I can write as h over hn over 2 times L. If I want to do this in 3 dimensions, I can write px is equal to L times nx over 2L, h times nx over 2L. Py is equal to h times ny over 2L. Pz is equal to h nz over 2L, just as you might expect. My allowed energies, of course, will be E sub n will be p squared over 2m. I can write that as h squared over 8ml squared, nx squared plus ny squared plus nz squared. Okay, this is getting a little abstract. What we would like to do now is maybe draw a picture of this and see if we can't get a better handle on what we're trying to do with this so-called particle in the box. Fermi electrons in the box. So this is what we do. Let's picture a graph in 3 dimensions, a sphere. But it's going to be a sphere in n space. So I draw this sphere, and let's let some vector n correspond to a point in that space that has coordinates n sub x, and y, and z. So the set of all allowed states would form a lattice that would fill just 1 octant of the sphere. 1 octant, I guess, is about the cleanest way to draw it. Because notice the energies are nx squared plus ny squared plus nz. So we're only interested in positive values of n, x, ny, and nz, because negative values, when I square them, give me the same answer. So that's how many states we can have, and we have to be a little bit careful. We're going to have to multiply the number of states by 2, because you can have a spin up or a spin down electron in each state. So you're really allowed 2 electrons as long as one is spin up and one is spin down. So we'll have to keep this factor of 2 in mind as we go along. So as we add electrons to the box, they start at the lowest level, close there, and then they populate the levels that get farther and farther from the origin, in n space, so to speak. And so we're going to call the radius of this sphere, when we finally get to essentially the Fermi energy, we're going to call that radius n max. And so the Fermi energy then is going to be equal to h squared n max squared divided by 8mL squared. And so the total volume of this eighth of a sphere is equal to the number of lattice points enclosed, since each point is separated by a distance 1 in all 3 dimensions of n space. So I said we've got 2 spin orientations to worry about. So if I want to do this, I have to say, what are the total number of states? The total number of states in n would be equal to 2 times 1/8 of a sphere times the volume of that sphere in n space, 4 pi n max cubed over 3. Or put it all together, that gives me pi n max cubed over 3. That's the total number of states I have. So the Fermi energy could handle, or could be written as E sub f is h squared over 8m times 3n over pi v to the 2/3. Length squared is volume to the 2/3. Now notice, my energy is an intensive quantity because it depends on both n and b, and I have this ratio of n and b. So that's the way it should be. What's the total energy of all the electrons? Well, the total energy I can write as 2 for spin, sum over nx, sum over ny, sum over nz, E of n. And because the number of terms is so large, we're treating this thing as, we'll treat it as continuous. I can write this as a triple integral E of n, dnx, dny, dnz. Now this looks formidable, but don't panic, we can do this. First thing we want to do, of course, is convert this to spherical coordinates, since we're dealing with a sphere. So I'm going to write dnx, dny, dnz instead in the spherical way, so that's going to be n squared sine theta d theta d phi dn in that way. Now I'm going to integrate, so I've got 2 on the outside for spin, 0 to n max dn, 0 to pi on 2 for d theta, and then 0 to pi on 2 again for d phi. I'm only going the 1/8 of the sphere, remember, n squared sine theta times n. Well, the d phi and d theta angles all integrate to pi over 2, as we would expect. If it were a full sphere, it would integrate to 4 pi, but it's an 1/8, so it's 4 pi over 8 or pi over 2. So my d phi and d theta integrals go to pi over 2. And I'm left with the following integral. It looks like pi 0 to n max e sub n to the 4th dn. Which is pi h squared n to the 5th divided by 4 n L squared, or 3/5 n times my Fermi energy. So the average energy of these electrons, put a mean over it if I want, is equal to 3/5 the number of electrons times the Fermi energy. Now, Fermi energy for conduction electrons is probably about a few eV, but that's much, much larger than KT. KT is roughly 1 over 40 eV, so this is true. So the ratio of the Fermi energy to the thermal energy is kind of like comparing quantum volume to the average volume per molecule. So in this case, V over N is much, much less than VQ. That's the same as KT is much, much less than the Fermi energy. By the way, the temperature at which the Fermi energy resides is what we call the Fermi temperature. It's just equal to the Fermi energy divided by Boltzmann's constant. It's in metals, it's a very, very, very high number. Virtually all metals would liquefy before you ever reached the Fermi temperature for those particular metals. Might take it a step further. We might ask ourselves, what about pressure? How does pressure figure into this? Well, I can write pressure as minus dE dV at constant S and N, which I can write as minus d dV 3/5 N H squared over 8m 3n over pi to the 2/3 d to the minus 2/3. Take the derivative of that, and I'm going to get minus 2 times n times the Fermi energy divided by 5V, or 2 times the mean energy divided by 3 times V. This is what we call a degeneracy pressure. And it's positive since when you compress a degenerate electron gas, all the wavelengths are reduced, the energies of all the wave functions increase. This pressure is what keeps matter from collapsing to offset any collapsing that would occur because of electrostatic attraction between protons and electrons. On a larger scale, it keeps white dwarfs from collapsing upon themselves. The degenerate electrons in a white dwarf allow the star to stay in place instead of contracting to nothing. So normal value of degeneracy pressure for metal is a few billion pascals. It's very hard to measure because we can't measure the effect because it's canceled out by the electrostatic forces that hold the electrons inside the metal. One thing we can measure, though, in conjunction with this is what we call the bulk modulus. The bulk modulus is defined as a change it's basically a change in pressure divided by a fractional change in volume. We write it as minus V dP dV at constant temperature. And it's roughly, in this case, it's going to be about 10⁹ times the energy divided by the volume. We might be interested in temperatures that aren't quite zero. And one of the reasons is you can't compute a heat capacity at zero. So we ask ourselves, suppose we wanted to go to maybe a temperature that's just slightly above absolute zero. So if T is the temperature, we would think that all particles would acquire some energy that would be on the order of kT. But in degenerate electron gases, if electrons acquire that small of an energy, they might try to jump into already occupied states, which they can't do because of the Pauli exclusion principle. So what happens is the only electrons that can acquire that energy of kT are the ones that are very, very close to the Fermi energy. So they're within kT of the Fermi energy. Otherwise, that won't happen. So we have to ask ourselves, how many of those electrons are we talking about? Well, it's got to be proportional to temperature. It should also be proportional to how many electrons you have. And so we would expect that additional energy required to go from T equals 0 to T equals something above 0 is doubly proportional to the temperature. So we can say additional energy times the number of affected electrons times the energy acquired by each electron might look like this. It's going to be proportional to NKT, that's my additional energy, KT, my additional electrons. Therefore, it's going to be proportional to something like N times the quantity KT squared. Well, what is this constant of proportionality? That's a challenge. About the only thing we can use, it's got to be something on the order of energy. It's got to have dimensions of energy. And about the only thing we know, I mean, we're doing this sort of back of the envelope. The only thing we know that has dimensions of energy is the Fermi energy. So if we divide this by the Fermi energy and multiply it by some constant, and it turns out, through a lot of extra math, the constant will turn out to be pi squared over 4. If we do that, we're there. So what this says is, if I take my energy, it's going to be equal to 3/5 my average energy plus this new term that I have to add, pi squared over 4, that constant that was determined, and kT squared divided by my Fermi energy. If that's what my mean energy is for a temperature that's slightly different than absolute 0, I can write my heat capacity as dE dt at constant volume. That being the case, I'll get pi squared n k squared T divided by 2 times the Fermi energy. Now this does approach 0 as T approaches 0, and it approaches it linearly, no less, which is kind of nice. That's kind of cute. All right, it's only a ballpark estimate. How do I quantify this? Let's go back. To the density of states. I can write U as, we're using E, sorry. E is pi integral from 0 to n max d of n squared dn. Let's change variables though from n to e. I know that e is equal to h squared over 8m L squared n squared. Therefore, I'm going to write n as square root 8m L squared h squared times the square root of e. And therefore, dn I can write as square root 8m L squared over h squared dE divided by 2 square root of e. So E then, I can write as 0 to the Fermi energy, epsilon of E, pi over 2, 8m L squared, h squared, to the 3 halves, square root of E, dE, at t is 0. Now this bracketed quantity is the number of single particle states per unit energy. So if I want to compute the total energy, I got to carry out a sum of all the energies in question times the number of states that have that energy. And to do that, I'm going to define, as we've done before, a density of states. Remember we used G of n to define the density of states. This time we're going to do it in terms of energy. G of E, number of single particle states per unit energy, is pi 8m to the 3 halves 2h squared v times the square root of e, which I can write as 3m over 2 ef to the 3 halves square root of e.
Dr. Blows, we have 1 minute left.
Important point here, G of E is proportional to the square root of E for a dimensionless, 3-dimensional box of free particles. Let's pick up with the density of states next time.